A quick review of the idea of discrete and continuous. Thinking back onto some algebra, a discrete graph could look something like this, where we've got a series of points. Maybe they're linear, maybe they're not, but they're not connected. So an example of that might be buying gumballs out of a gumball machine. And let's say for a quarter you get 2 gumballs. But there's no way to put 12.5 cents in and buy 1 gumball or 3 gumballs or something like that. So I can buy 2 for 25 cents, 4 for 50 cents, 6 for 75 cents, but there's no in-betweens on that. So the numbers cannot be fractioned. Versus a continuous graph. And I'm just using graph to illustrate the idea where it may have endpoints. It may have 1 point that goes on forever or 2 points that goes on forever. But there are fractions in between. There's an infinite number of points between any 2 points, so it can be fractioned. Can be fractioned is the idea that I think of with continuous. So maybe the example for that is buying beans at the grocery store, not in a bag, but in like one of those open bins, and you're just getting, you can buy a quarter of an ounce of beans, or you could buy 20 pounds of beans, right? Or any number in between within the weight of a bean, yeah? Something like that, or rice. Okay, so given those 2 ideas, let's talk about a discrete random variable. A discrete random variable must satisfy 2 requirements. Requirement number 1 is every probability p is a number between 0 and 1. Every probability p is a number between 0 and 1. And the second requirement is the sum of the probabilities equals 1. Discrete random variable. A great example of a discrete random variable is rolling a die. A die gives a discrete number of outcomes. You can't roll 1.5 on a die. It just doesn't exist. It won't stop at 1.5. There's no 1.5 on it. All right, so we're going to look at a problem. Page 469. It's not one of the problems in your problem set, but it's 7.1. And it's roll of a die. A roll of the die. Roll of the die. The first question, A, is what's the probability that we roll a number less than 3? So what are the possible outcomes that are less than 3? 1 and 2. What's the probability of getting 1? And the probability of getting 2? We're talking about one roll, but 2 possible things that would be successful. So is that a independent or dependent event? One roll, that's dependent. It's dependent because the die knows it has some knowledge of the other number on the die. So this is dependent. We would add those two to get 2/6 or 1/3. Does that make sense? Okay. The answer? Yeah. 2/6. There's 2 numbers we want on the die in one roll, 6 possible outcomes. I'm going to add to the question. What if I asked also the probability that we roll a number less than or equal to 3? How does that change the question? 3/6, right, because you've got 3 things now that would satisfy that thing. What I want to point out with, and the reason that I asked that second question is this. When we talk about less than and less than or equal to in a discrete situation, it changes the answer. In the next situation that we talk about, a continuously random variable situation, it does not. They have exactly the same response. Okay? I'll kind of explain that here in a minute, but I want to point out that for discrete, these guys play a role. All right, the next question asks us to do something in the calculator. So I'm just going to show that to you because there's kind of a cool thing in the calculator. If you'll turn your calculator on. Let's go to our lists and clear out anything that you have in your list. And we want to simulate rolling a die 100 times. So I'm going to show you a couple ways you can do this. Using the methods that we already know, we can go up to the very top of the list, L1 or L2 or wherever you're at, and we can go to math, probability, random integer. Not random integer, no repeat, because when you're rolling a die, numbers can repeat, right? So we want random integer. Our lower number is 1. The upper number is 6. And we want to put in 100 numbers. So, everybody okay with this? You guys with me? I got a head shake back here. You got it? Oh, something's going on. Get rid of that. It is a little tough, but there you go. All right. So go ahead and paste that in there. And what you would do with that then is you would want to sort those from smallest to largest or largest to smallest, whatever you want to do. So we're going to go stat sort A is going to be smallest to largest. What do you want me to sort? Well, L1, of course. And we'll look at that. And I now have 100 digits in my L1, starting with my lowest numbers, my ones. And I can count how many ones, and then I can count how many twos and number threes and so forth. But there's a more fun way to do this in the calculator. So let me show you how you can roll a die however many times you want. Okay. So, and it's far easier than counting it in a list. It's all right. So, go ahead and quit that. I hope all the calculators have this now. We had some trouble earlier today. If you go to apps here, so next to math, go to apps, and you want to pick probability simulation. Yours only has finance? Does anybody else not have probability simulation? I could program yours if you want.
Where we go?
Anybody else? Okay, so choose dice, roll dice or dice. Roll dice. And here's what you can do. Let's go ahead and press roll. And that's going to be window is what you do. So these 5 keys across the top. So it rolls a die. Now, we want to roll it 100 times. So what I'm going to do is I'm going to go 10 times for the single rolls. It's counting up here. And then I'm going to go over to the 10 plus. That means it's going to roll 10 times in a row. This is funny. In the last class, I was able to roll 30 before I got a 1. Let's see how far I go. Oh, okay. So I'm going to take that up to 50, 10 at a time. And then I'm going to bump over here and do 50 plus and just run that up to 100. So now I want to see how many times 1 rolled. Is it working for you? Yeah. So I just arrow over, and it tells me the frequency of 1s. So I got 20 ones. Yours is, I'm sure, different, or could be this 16, 19, 13, 14, and 18. So probability would say that we would expect the same amount each time, right? But that doesn't necessarily mean that that's what's going to happen. And this does a pretty good job of showing it. It's kind of like a horse race. So let's say we want to roll a lot. So if I want to roll a lot, I could do the 50, 50, 50, or I could do this. I'm going to escape here. Go to escape, right? Go to set. Escape and then set. Now, this trial set is set for 1 roll at a time. Let's make that 500. Okay? Yeah. Then I'm going to press OK. Now, let's see. I think I can... No. Okay, thank you. All right. All right, I'm going to go back in here. I want to start with an empty screen here. 500. Okay. All right, so I'm going to roll, and it's going to roll 500 times. It's kind of like a horse race. Should we bet? Let's make some bets. Get your quarters out. No, I'm kidding. I bet on number one. Okay? So most of them are in the 80s, almost 90. Now, I can do that again and again. What sort of shape would you expect to get? It shouldn't be a normal curve at all. It should be a, right? Because we should have equal numbers of each one. But that's not necessarily the case. But the more times we roll, the closer that's going to become to being a uniform sort of cubic shape. Whoa. Getting pretty close. I'll do one more roll, see how it looks. I think number one's going to win. That's just my... Yeah. I think I'm wrong. I think number 6 won. So, yeah, there are lots of interesting things in here, but this can give you the ability to, kind of in a fun way, get these frequencies. So we need to set that aside for the moment, and let's go on to the next idea. The next idea is a continuously random variable. A continuous random variable considers all probabilities in an interval. Okay, thanks. Considers all probabilities in an interval. And you're gonna like this. This is gonna look familiar. Remember our old friend that we haven't seen in a while? Right? So you guys will know the answer to this. What's the probability that in a situation where I'm between -1 standard deviation and 1 standard deviation, how much data falls between these two? 68%, right. So if this is my interval, I have a probability of 68% between those two standard deviations, where x takes all values in an interval. So that means x can be 0, it can be 0.5, it can be 0.99, it can be 1, it can be negative 0.63, it can be negative 15/16. So it takes all values in an interval. And something that I want to remind you of, standardize. Yes, please. Is z equals x minus mu over sigma. And I mentioned when we talked about this that that was technically over the square root of 1 because we have a sample size of 1, but you don't need to put that into your calculation. I just want you to remember that for some future stuff that's coming up. Okay. So let's look at a problem. But unfortunately, the example that I'm going to give you is one of your problems for the day. So if you put it in the notes, that's fine. But it doesn't deal with the standard curve. But you do have problems that do. So remember, when in doubt, standardize. So on page 475, it's called continuous random variable number 1. I guess there's a number 2 somewhere along the line. And it asks us to refer to a drawing in a previous part of the book that looks like this. So instead of having a curve, we'd still call this a curve, but it's not. It's a uniform curve, I guess you'd say. What's the amount of area under any probability curve? 1, right. So if this has a width of 1, what's the height? It's also 1, right? So let's see if we can use this block to answer some questions. A asks us, what's the probability that x is less than 0.49? So if I were to sort of somewhere put that 0.49, maybe about here, and I'm looking for this side, what's the probability that it's less than? Yeah, Ingersoll? It'd just be 0.49. Yeah, 0.49. Remember, also, when you use table A, I'll see if anybody needs one. I've got plenty of copies. But when you use table A, it always gives you the area to the left. So it's always the less than. So B asks us, what's the probability when x is less than or equal to 0.49? It is still 0.49, right. Where in the discrete random variable, the less than or equal to have different meanings, here they're the same. In algebra, we would graph this with a dotted line, remember? This would be graphed with a solid line. But in statistics, statistics doesn't make a distinction, because statistics says that the actual line itself holds no area value. So it has a value, the line itself has a value that is nothing, okay? So it doesn't matter how this is asked, the answer is the same, okay? Where in other maths it could be different. C asks us the probability that x is greater than 0.27. Right. So what we have to do is we have to consider the whole area of the block, 1 minus the 27, which gives us 0.73. That's correct. Good, Lexi. So anytime we're talking about a greater than situation, it's that 1 minus. That 1 minus turns up a lot in this class. Any greater than, more than, whatever. D asks us, what's the probability that x is between 0.27 and 1.27? Anybody see a problem with that? Yeah, you're right. We can't have a probability that's greater than 1. So if we can't go greater than 1, we actually use 1 for that 1.27. I'm just going to change that to 1. So it turns out that the answer is exactly the same as this one. Where you might be tempted to say there is no answer, in this case you just go, well, I can only go to 1, so I just go to 1 and call it good. Okay. Yeah, a little crazy, isn't it? E. Probability. 0.1 is less than or equal to x is less than or equal to 0.2, or 0.8 is less than or equal to x is less than or equal to 0.9. Or is a what kind of word for us? What does it indicate that we should do? Addition, right. So the area under the curve that's between 0.1 and 0.2 would be 0.1, yeah. And the area under the curve that's between 0.8 and 0.9 is also 0.1. So the answer to this is going to be 0.1 plus 0.1, or 0.2. Heather, you okay with that? Yeah. Yeah? All right. We have two more, F and E. F. F asks us, says the probability that x is not between 0.3 and 0.8. Well, how much area is between 0.3 and 0.8? 0.5. So how much area must not be between 0.5? Yeah, 0.5. And E. The probability that x equals 0.5. It's not. Oh, you're right, it is G. How did I go from, I can't spell or write letters, apparently. I don't know my alphabet. G, okay. All right. Hey, at least you know what you get with me, right? Okay. So what's the probability that x equals 0.5? It's a good thought. It's actually 0. Here's why. If you think about what are all the possible numbers that I can reference between 0 and 1, isn't there an infinite number of fractions that I could split up in there? So 0.5 is just 1 out of infinity. And for those of you that might have taken calculus or pre-calc possibly, what does 1 out of infinity approach? 0. Yeah. It's about as close to 0 as you can get with a fraction without actually being 0, so we just say it's 0. So it's such an unlikely event, we just call it 0. That's how, at least that's how I make sense of it, why that would be 0. Okay? All right, so